Welcome back. Today is an exciting day because I'm kicking off a new series where I teach you how to use one of my favorite robotics simulators, Drake. This is a very powerful simulator, but in this video you'll just learn how to simulate a simple continuous time ordinary differential equation using Drake in Python. In just a few videos you'll be able to build, simulate, and control your own robot in Drake. So if you haven't installed the Python version of Drake on your computer yet, just be sure to watch my installation video linked in the video description below. Let's get started. Given some ODE, we can always represent it in some state space format, x dot equals f of x and u, where x represents our state vector and u represents our system input. By writing just a few lines of Python code, you can use the simulator inside of Drake to simulate your system given some input signal u and some initial condition x naught. You will also see how to use matplotlib to create an interactive graph like you see on the right, but in future videos you'll also learn how to create a 3D animation of your system using Meshcat. So at a high level, there's a few steps you'll need to complete in order to simulate your ODE. In Drake, we simulate a diagram, which is a collection of systems that are connected together with input and output ports, just like Simulink. To represent our system dynamics, we author our own LeafSystem, and then we connect input and output ports to our LeafSystem, so then we can apply our input U and observe our output X. So step one is writing down your ODE in state space format. I will use a sliding block system as an example. So denoting the position as x, the dynamics of the sliding block are going to be given by mx double dot is minus bx dot plus u, where m is the mass of the block, b is a linear friction term, and u is our input given in newtons. To convert this differential equation into a state space format, we're going to let x1 be x, the position, x2 be x dot, the velocity, and because x1 dot equals x2 and x2 dot equals x double dot, we can rewrite the ODE in state space format as a two-dimensional system with states x1 and x2. And for the sake of simplicity, let's just assume that m is 1 and that b is 0. Now the system is just x double dot equals u, which is also called the double integrator system. This is equivalent to modeling a block with mass 1 on a frictionless plane if you like to have a physical intuition behind your system. Okay, now let's create our LeafSystem. We create a new class called double integrator, which is derived from the LeafSystem class. In our constructor, we create an input port u of size 1, meaning that u is a vector of length 1. We declare a continuous state, which represents x1 and x2. We specify that there's one generalized position, x1, and one generalized velocity, x2. Then we declare a state output port called y, which just creates an output port and assigns the state vector x1, x2 to the output port for us automatically. Because we declare a continuous state, we must implement the doCalc time derivatives function. This function implements the state space dynamics by setting the value of the derivatives argument to the vector x1 dot, x2 dot. You don't need to memorize all the code here. You should just remember that our dynamical system is implemented as a LeafSystem, and you can write custom dynamics in the doCalc time derivatives function. Now let's create a diagram. We use a diagram builder object and then simply add systems to it. First, we add our double integrator, and then we add our input. We're using a constant vector source to output u equals -1 for all time, but you can replace the constant vector source with any other system, such as another LeafSystem or any of Drake's built-in systems, such as a sine function or a white noise generator. Next, we use the builder.connect function to connect the output port of our constant vector source to the input port of our double integrator. We also add a logger using the handy function logVectorOutput, which automatically connects the output port of our double integrator to the input of the logger. Finally, we finish building our diagram by calling builder.build. The two functions to really remember here are builder.addSystem and builder.connect. You'll get used to creating your own diagrams with lots of practice. Now that our diagram is built, we can create a simulator. The first 3 lines are used for setting up our initial conditions. In Drake, the word context is thrown around a lot, but at this point, just note that context contains the state and the timing information for our diagram. After setting the initial conditions, we create a simulator object and then run the simulator to time equals 5 seconds. When the simulator is finished, we extract the time and logging data. Alright, so now let's hop into VS Code and run the starter code that I provided. Okay, so I'm in VS Code looking at the lesson 1 starter code. If I go ahead and I run this file, the first thing that's going to happen is we're going to see this diagram of our system. So we have a constant vector source. Its output is connected to the input of a double integrator, whose output is connected to the input of this vector log sync. we'll go ahead and look at the position versus time. We see that we start at the initial condition of 1. That corresponds to line 72 down here of the continuous state. And then if we look at the velocity, we should see that the velocity is decreasing. That makes sense because our input is u equals -1. As a reminder, all of the code for this series is on my GitHub page, which is linked in the video description below. For you to really get a feel for Drake, I've included tasks for you to complete in each lesson. So let's do that now. So the first task is to change the initial conditions and the constant input vector to something else. So let's go ahead and do that. So line 72 is where we set the initial conditions. Let's just set these guys to 0, 0. And then let's go ahead, our u was -1, let's make it +1. And then let's run the code again, just to verify that our changes were made and the simulation's different. There's our diagram again. So here's our position graph. We see it starts at 0 and goes up. And our velocity graph, it also starts at 0 and goes up. This is linear, just as we expected. So we can move on to task number 2. For task 2, let's modify the system dynamics for our leaf system. We're going to use a mass of 2 and a damping coefficient of 0.5 so that the behavior looks like a sliding block with friction. So pause the video now and then unpause to see the solution. So the first thing we're going to do is go up into our do calc time derivatives function. And we're just going to want to edit this x double dot equals to u. We're going to make the mass 2. So we'll have 1/2. Then let's have a damping coefficient of 0.5 times x dot, and then plus u. Perfect. So we'll go ahead and run this. And the position graph looks pretty similar, but let's look at the velocity. So now you see the velocity is not quite linear anymore. This is because as we go faster and faster, the friction term is slowing the block down. For task 3, let's replace the constant vector source with our own controller, a LeafSystem, which outputs a sinusoid. We're also going to connect the output of our controller to another logger to plot the input to the double integrator. So pause the video now. Let's get started by copying and pasting this starter code from my GitHub page. So if we take that and we go back to our Python code, we'll just put this right in here. And all we have to do is modify this line right here. So u, instead of being 10t, we'll just do numpy dot sine of t. Next we'll go down here. So this vector input, I'm just gonna rename this guy. So you can just go rename symbol and call this controller. Then we can go here and instead of a constant vector source, we're just going to make our controller. We can get rid of this line. Okay, now let's add a new logger. I'm going to call this my input logger. Now at the end, we actually want to get this input data. So what we'll do is this. We'll just say our input log is going to be the input logger.find log. Then u is going to be the data. And we can just go ahead and make a quick figure. And let's run this. All right. So first thing to notice is our diagram changed. Now we have the controller instead of the constant vector source. We have a vector log sync for listening to this controller. And then we have our double integrator and vector log sync as before. Okay, now our position, this is definitely different, starting to go down here. And if we look at the velocity versus time, we have the same thing going on. So this is the control input versus time. So this looks like a beautiful sinusoid. In fact, let's increase the running time so we get at least 2 periods in here. So I'm just going to go ahead and change this advanced to method. Let's make this equal to 4 times numpy.py. And we don't really need all these diagrams, so I'm going to get rid of these and run this. Okay, so now here's our position versus time. Here's our velocity versus time. And then here's our beautiful control input versus time. So as a challenge, you can try to replace this controller with Drake's sine class. If you go to the documentation, you can read all about how this sine function works, what the inputs are, what the outputs are, how you create it. And if you're looking for the solution, you can find that in lesson1solution.py on my GitHub page. At this point, you're actually able to simulate any continuous time ODE in Drake. In the next video, you'll learn how to add state feedback to your controller so that you can apply PD control to the double integrator. If you found this helpful, drop a like and leave a comment to let me know. If you have any requests for this series, let me know about them. Be sure to subscribe so you don't miss the next video in this series. See ya!